Welcome back, everybody. In this video, we're going to learn about different ways that we can model alkanes. Alkanes are the first class of hydrocarbons and thus organic compounds that we're going to examine. For this video, we're going to use the example of a molecule of butane. And we're going to start off by looking at how we model chemicals in general. So the first thing you learn about when you learn about chemicals is usually it's chemical formula, which we build off of the elements in the periodic table. And we're going to do one for butane. We're going to write out the molecular formula for butane. And the molecular formula is probably the simplest way that we could represent a chemical. So when you write out the molecular formula for butane, butane has 4 carbons and 10 hydrogens. In the molecular formula, the only information it really tells us is that a molecule of butane has 4 carbons and 10 hydrogens, but there's not really much more that you can glean from that. For example, if I ask you to show me like in 3 dimensions what a molecule of butane would look like, there's not enough information in this formula to tell you how to draw it. And ultimately, that's something that we need to, that brings up the reason why we need to have other ways, other formulas to communicate that information. So with each formula that I'm going to show you, with each type of formula, we're going to get more and more specific about the chemical. So C4H10, this is a molecular formula, the molecular formula for butane, but here's a little hint, this could possibly represent another molecule. Okay, there is more than one molecule that the molecular formula C4H10 can represent, which we're going to look at in a future video called isomers. So butane has 4 carbons and 10 hydrogens, but now we have to ask ourselves, how are those atoms arranged in space in 2 dimensions? So the next formula I'm going to show you is the structural formula. And the structural formula communicates a little bit more information. The structural formula will tell us in 2 dimensions where each atom is oriented. And it tells us what atom is bonded to other atoms. So let's look at the structural formula for butane. Butane has a carbon backbone of 4 carbons, and then each carbon can make 4 bonds. Hydrogen can make 1 bond. So in a molecule of butane, the carbons, the 2 carbons on the ends, the terminal carbons, they make 1 bond to another carbon, and then they make 3 bonds to other hydrogens. The carbons in the middle are already bonded to 2 carbons, so that means they only have a capacity for 2 other bonds to 2 different hydrogen atoms. So here we see single carbon-carbon bonds. The terminal carbons are bonded to 3 other hydrogens because they have 1 of their bonds designated as a bond to a carbon. And then the carbons in the middle have 2 bonds to hydrogens because they have 2 bonds toward the other carbons in that carbon bridge. So this is the structural formula, because the structural formula tells us about the structure, and it tells us about where each carbon and where each hydrogen is in the molecule. It's a 2-dimensional molecule, so it's not really communicating the whole picture, but it does give us more information than the molecular formula. So once again, this is a structural formula. The lines that you see here, just a reminder, these represent covalent bonds. So that's a sharing of a pair of electrons. Okay, and then it's the same There's covalent bonds between carbons and covalent bonds between carbons and hydrogens. So we represent a single covalent bond with one line. All right, now with large molecules, and even for this molecule, I found this kind of tedious to draw. So there's another type that we can use, and it's called the condensed structural formula. And in the condensed structural formula, we're going to get rid of all these little carbon-hydrogen bonds. We're not going to show them the same way that we showed them here. We're actually going to smush it down a little bit more. And for this carbon here on the end, I'm going to represent it as CH3. Okay, so it's almost like I'm going to go back into this molecule and I'm going to like separate the carbons. They're not actually separating, but I'm going to separate those carbons. The first carbon here is one carbon with 3 hydrogens. Then I'm going to make a bond, a line, to the next carbon. This carbon has 2 hydrogens coming off of it. I'm going to draw a bond to the next carbon. This one also has 2 hydrogens coming off of it. And then I draw a line to the last carbon, but this one has 3 hydrogens coming off of it. So this communicates the same information as our structural formula, but it's a little bit more condensed, hence the condensed structural formula. I can even actually smush these a little bit, smush this down a little bit more, like an accordion. These CH2 groups are the same thing, so another way that you might see it written is this. You might see it written CH3 brackets CH2, and then a 2 subscript telling us that there's 2 CH2 groups in the middle, and then CH3 at the end. So there's your condensed structural formula. But that's not where I land. My favorite structural formula, and the one that you're going to see me employ the most, is the line structural formula. I love this one because it's the laziest one, but it communicates the same information as the structural formula and the condensed structural formula. In the line structural formula, I show bonds using a line, and the points on that line, or the vertices on that line, represent carbon atoms. So to represent this one, it has 1, 2, 3 carbon-carbon single bonds. So I'm going to go 1, 2, 3. And that's it. Each point on this line represents a carbon atom. So this would be carbon 1, there's carbon 2, carbon 3, carbon 4. Now, I don't show the red dots, the carbons here. They're going to be indicated by the points, okay, on this line. So this shows us a 4-carbon structure. With a line structural formula, I do not need to show the hydrogens, so I don't need to do this. We assume that the hydrogens will be loaded up on these carbon atoms. I don't write individual C letters to represent carbons, because those are represented by the points on the zigzag. The other cool thing about the line structural formula is that it tells us a little bit more about its geometry too. A carbon in this molecule here is going to have one bond to, let's say, hydrogen. I'm going to do the one on the end here, like carbon 1. It's going to have a bond to hydrogen. It's going to be bonded to another carbon, and then the rest of the molecule. But then it also has bonds to 2 other hydrogens, which are actually in 3 dimensions. And this carbon is in the tetrahedral. This is the tetrahedral geometry. And the thing I like about the line structural formula is it actually tries to communicate some of that geometry in the way we draw it. So we go with the zigzag because the molecule is going to look like it takes on this zigzag appearance because each carbon is in a tetrahedral arrangement. So that's the line structural formula. I like that one the most. and it's probably the one you're going to see me use the most. In the Nelson 2030 chemistry textbook, you're going to see this more often. But I'm showing you these different ways of writing them because you're going to need to think quickly between this structure and this structure. You're going to have those two things in mind, and even think in terms of condensed structural formula. I've written exams before in my undergraduate degree where professors would only use this structural formula, and then I've written probably more of them where they show all the compounds using the line structural formula. So, as I said, I tend to prefer this one, and you'll see me using that one the most. Okay. So this is how we can model alkanes. This is the same thing. We can model alkenes the same way. There's some variations in how we draw them, but for the most part, these are the types of formulas that we're going to see. Now, I said that this molecule here is butane. It has 4 carbons. And I'm just going to make a quick note here. There's a whole list of rules for how we name these compounds, and that's what we're going to look at in the next video. But I'd encourage you to have a look in Genius at the list of rules I posted in there. That goes over kind of the naming conventions and the root names that we give for these types of molecules. So I said this is butane. There's a whole list of those types of roots that you need to memorize. So because it has 4 carbons, it gets the root name but. So I'm just going to briefly go over that list. The word but comes from how many carbons there are in its main chain. So if you have 1 carbon in a chain, your root is meth. So if just carbon right by itself, the root is meth. If you have 2 carbons, the root is F. 3 carbons, the root is prop. 4, as I said, the root is but. For 5, it is pent. 6 is hex. 7 is hept. 8, you could probably guess this one, it's oct. 9 is non, and 10 is dec. So this is a little bit like learning, how to name ionic compounds and covalent compounds, but you'll just have to memorize this. In Chem 30, you do need to memorize this because this table does, I believe it doesn't show up in your data booklet, but it's not that difficult to memorize. There's a useful acronym for the first four here, like most engineers prefer blondes or brunettes or whatever, or you could pick something that's maybe a little bit more socially acceptable nowadays. I don't care. MEPB. I've tried for years trying to think of like what's some sort of acronym that you could incorporate for all 10 of them. So I'll give you a little challenge. I'm always looking for useful acronyms for memorizing this type of stuff. If you can think of one, let me know. Maybe post it in the comment section, or just email me with what you think. All right, I'll see you in the next video, and that's where we're going to learn about how to name these alkanes. And we're going to use this list here. All right, see ya.